So project number 5 is due on Friday at noon. Of course, then the final exam is Wednesday, December 12th at 10 a.m. in this room. Now, I anticipate that we will actually finish the notes and also a review for the final next Tuesday. So, unless there's any objections, we probably won't have class next Thursday. Okay? So, since I anticipate that we will finish on Tuesday, that means we'll do the final exam review on Tuesday. Please come prepared to ask questions if you have them on Tuesday. Also, before we get going here, my office hours will end today about 1:20 because there's a presentation that I'm going to attend at 1:30. So if you need to come talk to me, please come talk to me after class. Are there any questions before we get going here? Okay, we left off on page 18 in the notes. We're going to talk about something called robust regression. This is helpful to use when you have influential observations and you have really no good way of handling them. Now, the term robust in statistics is used to mean that a particular statistic that you are actually calculating doesn't change much if you have, let's say, problems with the data. Problems could be like, for example, outliers. In your very first stat course, you learn about the mean and the median. And you know that the mean can be a lot more greatly affected by outliers than the median. And so what we often say in statistics then is that the median is robust to outliers in comparison to the mean. Well, now we're going to apply this idea of robustness now to regression models, meaning we want to estimate beta 0, beta 1, all the way down to beta sub p minus 1. And we want these estimates to not necessarily be to dramatically, let's say, change due to, let's say, an influential observation. And so we're going to look at ways in that we can estimate our model so that these estimates, our B's, don't change a whole lot due to these influential observations. Okay. So the way that we've been estimating our B's so far is through what's called least squares estimation. And again, what we're doing in this kind of a situation is that we want to minimize the sum of I equal 1 to n of yi minus y hat sub I squared. Find the B's that minimize our sum of squared errors. But why should we use this as our criteria to choose what estimates of what the estimates are for beta? Well, we don't have to. There are other criteria that we could choose as well, and these lead to estimators that are no longer least squares estimates, but instead something else. So notice how we square these errors, these deviations, you could say. We square them so that they're all positive. Because if we don't do that, then the sum will end up being 0. So the sum of yi minus y hat sub I actually ends up being 0. Well, we don't have to square to get this to be positive. Instead, what we could do is just simply take the absolute value instead. And now minimize this in order to find your parameter estimates. No, you'll see in some plots. I think to some respect, this square magnifies differences more. And this is called least absolute residuals regression. Okay? We could also use what's called iteratively reweighted least squares, or IRLS for short. And this is just basically weighted least squares like what we've seen before, where we have weights now associated with every single observation. But how about we choose the weights in a way such that we put smaller weights on observations that are, let's say, different from all the rest, and put bigger weights on observations that are similar to all the rest. And that's one way to think about how IRLS works. And in fact, IRLS is used to estimate generalized linear models. So if you take Stat 875 or Stat 971, you'll learn about this in a lot more detail, and so I'm not going to discuss this here. What we will focus more on are the next two. Least median squares regression. Now this is kind of different from what we've talked about. Now what we're going to try to do is minimize the median squared residual versus the sum of the squares. And we've talked about how I mentioned at the beginning, how the median is more robust than the mean. So you might be thinking, okay, well maybe if I look at just the median of these residuals instead, that might work out to be better, more robust. Another thing that you could do is what's called least trimmed regression. This is to motivate this. Some of you, maybe in another class, have heard of something called a trimmed mean, where normally when we find means, let's say I have n observations, you take the sum from I equal 1 to n of the y sub i's. Instead, what you could do is take, let's say, the middle q observations and just find the median of those. Find the mean of those. So if I were to do a plot similar to what we've seen before in terms of a dot plot, suppose I have values of y sub I on the y-axis, and I look at a plot that looks something like this. Notice how I have kind of two outliers at the top. Well, what trim mean would do is say, okay, let's maybe trim off the top two, trim off the bottom two, and just find the mean of these. And so what least trimmed squares regression does, it says, okay, let's look at the middle q of our residuals on the absolute value, square it, and use this as a criteria to minimize, then to find our estimates. Now, you might be thinking, well, why don't we just use these methods all the time? Well, the problem is they're not as easy to work with. In particular, when we were working with least squares estimates, I could actually give you a nice little equation for B0, B1, B2, and so on. Here, we're not going to be able to do that. Iterative numerical procedures are needed to actually do this minimization and to find what the estimates are. Okay, let's take a look at an example to help explain these ideas a little bit better and why they work. I decided just to simply you look at the example that's in the book and add some additional details to it. And what they look at is a data set where Y is the average mathematics proficiency for a state. And so what we actually have for observations is information from 40 different states, or I should say states or territories. I don't know why they didn't have data on all states, but they didn't. And so our sample size is 40. And X2 is the percent of students with several reading sources. You can look at the example more in the book if you want more details what that means. And we're simply going to use this one particular variable, X2, in this data set from the book to estimate Y. And so what I'm going to do is read in the data. The data is, it comes with the book, of course. This is the data file. Now, as you've noticed with these data files that come with the book, they don't have the actual variable names at the top, as in the first row, even though they're just ASCII text files. So I say header equal false, and then I use the call.names argument to actually give it the corresponding variable names. And so this is what it looks like at the beginning. So for example, here's Alabama. The mathematical proficiency is 252, depending upon whatever scale that they're measuring on, and home lib is 78. So let's just simply, and I guess I can go over to Word for this. Let's just simply estimate the model, a first order model, and then we'll look at a second order model as well, using regular old least squares, just to see what would happen. So, I estimate the model like normal using the LM function. So here's my first order model. Here's my second order model. Notice I'm putting the first order model in mod.fit 1. Second order model is going into mod.fit 2. And then I do some plots. Also, sorry, I'm getting ahead of myself. Notice that we have marginal significance for the squared term in the second order model. In the first order model, we do have significance for just the first order term. So let's look at some plots. So what I decided to do was use my examine.mod.multiple.final plot function that we saw in chapter 10. And what I have here is for the this is for the first order model on page 1122. And let's just focus on, just to save time here, let's just look at the second order model results. So we're going to focus on second order model more here. And this is what we get. So do I have any potential outliers? Yes, I do. Number 36. This is the Virgin Islands. Okay. Now, since this is a territory and not, a state, you might think that there might be some differences between the Virgin Islands and the regular old 50 states. This is kind of being shown here by it being an outlier, or as you can see, potentially influential. So look at my DF fits. There's number 36. Ooh, look at this one, number 11. This is Washington, D.C. Now, obviously, in the news over the last few years, there's been a lot said about the D.C. educational system. Unfortunately, often it's negative. So it's not necessarily surprising to see that this is out there as being potentially influential. We see some DF betas pop up as well. I'm sorry, 11 was Guam, not Virgin Islands. 11 was Guam, or I'm sorry. Yeah, 11 was Guam. Excuse me. 8 is DC, and yes, look at there is DC there. The main point is, if you look through all these plots, and the ones that I've labeled here, notice how 3 of them are not normal states. In particular, Guam and Virgin Islands, I'm not surprised to see these stand out because obviously they're quite a bit different than the regular 50 states. I'm not surprised by DC either. California, well, that's California for you. And it's only popping up once. Anyway, though, okay, so we've seen what's happened now with our regular old diagnostic plots. So we're starting to get a little worried about our model here. So how about we do some plots of our model too, since we only have one predictor variable. So you do the usual scatter plot using the plot function. I use the curve function to plot the first order model. I use the curve function to plot then the second order model. And then, if you remember the identify function, I use the identify function for our specific X, home lib, specific Y, math proficiency, and I identify them using these labels, the state. So before, we've always used just observation number. Well, it makes sense to use state here. I put a nice little legend on the plot, and this is what we get. So we can see, through me clicking on the plot, Guam, DC, and Virgin Islands. they stick out a lot from the rest. And in fact, and we're again going to be focusing on the second order model. And if you were just to kind of ignore these three observations, what do you think would happen to the second order model? Well, you might be thinking, well, it's probably going to go more through the middle of those points. Still, definitely a second order model is needed, but it will go more through the points. And so you can see the potential influence that's occurring by these states or territories dragging down everyone else. In some respect. I mean that joking. Sorry if there's anybody from Virgin Islands, Guam, or DC here. When I was preparing for class, then I thought, well, how about we actually look at what would happen if I remove these three observations from the data set. Because if you remember in Chapter 10, we talked about one way to handle influential observations, and that is to limit your population of inference. So that what we could do here is actually remove all observations corresponding to non-states and just limit our population of inference then to just states. Because what happens elsewhere is different from what's happening to regular 50 states. And that's a reasonable approach that one would follow based upon what I told you in Chapter 10. So what would happen if I actually did do it? So this is not in the notes, since I did this before class. So I estimate the model. I put the results into something called mod.fit3. And again, notice how I remove those particular observations. So the data is in table 11.4, and I put a minus there, and I think we've seen this before. I put a minus there, combine observation 8, 11, and 36 together. So that negative says take them out of the data set. And I estimate my model, and I plot the model. So let me highlight some of the code beforehand so we can actually see that. Don't want that. Sorry, I got all these plots. Perhaps this has happened to you a few times through running my function. Okay. Just give me a second. Okay. So although I don't have this represented in the legend, the dot dash line, the blue, that's the model that we get when we remove these three observations that are highlighted on the plot. So you can definitely see why these other observations are influential. It changes your interpretation of what's happening there. So this would be one way to handle this problem based upon Chapter 10 stuff. Another way is to use robust regression. Okay. The function that we're going to need is called LQS to do robust regression. It's in the mass function, the mass package of R. We've seen the mass package before. It automatically comes downloaded and installed in R, so you don't need to download it yourself. And the first thing I'm going to do is this least median squares regression. And the way that you use the function is very similar to the LM function. You say LQS formula equal, put in your Y, your X, X squared, put in your data, but now say method equal LMS. The results go into mod.fit.lms, and if I just simply type mod.fit.lms, this is what we get. So here's B0, here's B1, and here's B2. So you can write out your model just like how you would normally. However, you're just using a different way to estimate the parameters. These scale estimates, these are two different ways to estimate the square root of MSE. You can look at the documentation if you're really interested in it. Unfortunately, though, with this function, it doesn't allow you to then use the summary function to summarize the results in much the same way that we did with LM. So when I say summary mod.fit.lms2, this is what I get. And not very useful. It just describes the information that's actually stored inside of this, this object. Let's look at least trim squares.
How do you do predictions?
We'll do that shortly. Let's do least trimmed squares regression. The exact same code, except for I put method equal LTS there instead, in quotes. So here's B0, here's B1, and here's B2. Let's do some plots now to do some comparisons here. So this is pretty much the same kind of code that I had before, except for now I'm going to plot these other kinds of models. So I do a scatter plot of my data. I put the second order model from least squares regression on it first. Then I put the least median squares, there's the LMS there, and then I put the least trim squares. I use identify again, and I put a nice little legend. And this is what we get. So the red line here, the dark red line, that's the second order model estimated from least squares regression. And it's hard to see, but indeed there are two lines that are almost quite overlapping one another. And this corresponds to least median squares and least trim squares. And you can see how they agree.
Are there measurements beyond Texas and California not counting below?
What do you mean? I'm sorry.
Are there points to the left?
No, there aren't. I only identified, I just clicked on certain points just to identify them.
Yeah, I understand. I mean,
This is all the observations. And so you can see, and this is the main point of this section, you can say, you can see how these other estimation methods are not as affected by these influential observations. And that's the whole goal of using a procedure like this. Then before class, since I, had estimated the model without those three observations, I thought, well, how would this model now compare to what we get from the least trim squares and the least median squares? So let's just quickly do that plot. And now I'm going to add this other line from for least squares regression without those three observations. And you can see how they're quite similar. So they are kind of achieving the same end result. And they're not exactly the same, but you see that they are trying to do something very similar. Okay. Yes?
Today, all the methods have unbiased. Are they all unbiased for estimators of the coefficients?
That's a good question, and to be honest, I don't remember necessarily seeing a proof. What I would think, and I apologize, I don't know this off the top of my head, I would think that they are what's called asymptotically unbiased, meaning as n goes to infinity, you're getting to the right spot. I would think that, but I'm not 100% sure. But that's a good question.
it's interesting, by the way, the chart. That basically, this means overcompensating. If you remove the points, you get lower chart.
Yeah. And I mean, that's just the effect of outliers. It all comes back to the same idea from your first SAT course where you looked at the mean versus the median. Same idea. And and just to make sure you understand this, why are we more interested in these top models versus the bottom model here? Because again, the big picture is you want to understand the relationship between X and Y, and you don't want one or two observations to unduly affect your interpretation. Okay, let's make sure that I talked about everything I wanted to here. So let's go to page 1128.
Estimation of say confidence interval.
Yes, it is, and I know you had that question regarding the prediction. Well, first of all, I think you asked, well, how do you get a y hat? Is that what your question?
Oh, whoa.
Well, y hat wouldn't be
Y hat is
difficult,
pretty
but now the confidence intervals and prediction intervals, like let's say for y, and let's see, let's try this. Just give me a second here. Usually when I discuss these models in class, it's at the end of the semester, as it is now. And the book really doesn't go into some of these details, and so that's why I just I don't necessarily discuss them, and I don't discuss prediction in here. Let's see, what's the function I want? Yeah, it doesn't look like it automatically gives you the confidence intervals and prediction intervals. I guess I hadn't necessarily done this in R before.
Considering that you don't have one value for MSE, doesn't really surprise.
Yeah, well, I could use one of the two. I'll check into a little bit more how this is done in R. Maybe I missed something here. The problem that you're going to run into is that the actual equations are not going to be as nice as they will with least squares, and so that could be why they're not programmed in at this time into R. Okay, let's see. So that concludes then that particular section. I think we discussed everything on 1129. At least I guess with respect to the last example, I think if I had a preference, I probably would simply remove those three observations. That's at least the way that I would have done it. And part of the reason, and we kind of see this here, is that we have all these nice tools available to us already with the LM function, stuff that results from the LM function. And so it's often easier to do that versus go to one of these other estimation methods, unless it's absolutely necessary. Okay, so page 1130. We're going to talk about something called nonparametric regression. In particular, we're going to focus on something called the Loess method to estimate a nonparametric regression model. In most places, you will not see this W listed in there, and it still will be pronounced Loess. but our authors will actually put the low and then S there. Now let's first begin with a discussion of what's the difference between parametric statistics and nonparametric statistics. Parametric statistics. What you're doing is first beginning with some kind of distributional assumption. Maybe Y is distributed normal. With nonparametrics, I'll just abbreviate with NPAR statistics, you don't have a distributional assumption. So that's the difference between the two. Or strict or fully nonparametric statistics, you don't have a distributional assumption for your data. And so we're going to look at something called nonparametric regression. It's not fully nonparametric, but it's close to being fully nonparametric, but not quite. And the reason why we want to do this is at times, our normality assumption for our Y with our regression model might not be very good. And so this provides you another avenue then to follow if needed to work with a regression model. But by getting away from this normal distribution assumption, and actually to some respect no distributional assumption at all, to some respect. You'll see where the distribution assumption does come up a little bit later. You actually end up giving up some things. In particular, the ability to interpret your model as easily as what we did from Chapter 1 through Chapter 10. Okay, so let's talk about the Loess method. What we basically do is this. For every, think of this, for every observation or data set, how about we just pick one observation out? And find similar observations to it in the data set. Fit a regression model to just those similar observations. That's it. Get a y-hat out. Go to a new observation or data set, find similar observations to it, fit a regression model just for those observations, and get a y-hat out. Do that for every single observation or data set, and that's your y-hat that you get for your model. Unfortunately, though, you're not going to be able to actually state one overall regression model like what we've been doing for an entire data set. So here's maybe a little better description of this in terms of a visual description. So let's say that we simply have one predictor variable x. We have a response variable y. And we're interested in the particular observation that I have circled there. To do Loess regression, then, what we need to do is find similar observations to the one that I circled. Well, how do you quantify similar? Well, predictor variable values that are quite close to it. So how about we take the three nearest neighbors to this observation, which would be, let me use my highlighter here, this one, and this one. Take those three nearest neighbors, estimate a regression model to just those three observations. So use x to predict y. Get your y-hat out from that particular regression model, and that's the y-hat then that we're going to use for the circled observation. Just to emphasize the point here, suppose instead maybe we were over here. And if I want to find the three nearest neighbors, it would be this one, and this one. Fit a regression model of those three observations, get a y-hat out, and that will be the y-hat for this particular observation. So essentially what you get is a whole bunch of y-hats, but you don't have one b0 and one b1 to interpret for the relationship between x and y. And that's what you lose out on when you do this Loess method. Let's extend this now to a case where you have two predictor variables. And so what I've done is actually graphed, let's say, two predictor variables here. I put observation numbers there. I don't graph y at all because that's not factored in to deciding what's a nearest neighbor. And if we focus in on observation 1 here, oops, let me circle it. And let's say I want to find the three nearest neighbors to it. Well, you can kind of get an idea from just looking at the plot. Observation 6, 2, and 8. Fit a regression model to it. Then with the corresponding y. Get your y hat out. That will be your y hat for observation 1.
Something like moving average.
It's not necessarily a moving average. I mean, I see what you mean by you're kind of moving windows to some respect throughout, but it's not a moving average. And this is very closely related to stuff called nearest neighbor data analysis, you could say, and it pops up in a number of different places. So, for example, if you've taken Stat 873, you might hear something called nearest neighbor discriminant analysis. Well, this is very, very closely related to it. It's just a different way to look at a problem. But what you lose out on is interpretation. But if all you want is y hats to begin with, well, maybe this is a nice approach. Well, let's say that we have a situation where, let me actually go back up here. It's easier to talk about one predictor variable. You know, imagine this to be the high school and college GPA example. High school GPA, college GPA. And now you have, let's say, a new student who has applied to Nebraska, and so all you have is their high school GPA. How would you use now our model that we just constructed to figure out what their y hat would be? So that this observation is not in our data set itself. Suppose x was 4.0, and we'll just put 4 here, 0 there. What would you do? Find the nearest neighbors to x equal 4.0. Maybe 3 nearest neighbors would be this one. So now using those 3 observations, you get a y hat out. So notice now how prediction for new observations, new x's, is different from how we would do it back in chapters 1 through 10. In chapters 1 through 10, we would get one model, 1B0, 1B1, and you could throw out your data because you don't need it anymore. Here with nonparametric regression, this low S method, you can never throw away your data because you're always going to have to estimate new regression models whenever you have to do an estimation or prediction at a particular x. So you always need to figure out what the nearest neighbors are. So notice, again, just another difference from what we've been doing. So how do you quantify, then, nearest neighbors? Well, you need some kind of measure of distance. And it was quite easy through the plots that we were looking at to figure out, well, which observations are the closest to one another. But, you know, especially when you have 3 predictor variables, 4 predictor variables, 5 predictor variables, it's not going to be that easy. And plus, you know, you want an automated method to actually find these closest neighbors itself. So you need to be able to quantify distance as a numerical value. The simplest thing that can be done is to use a Euclidean distance. So simply, let's say that I'm interested in a particular, we'll look at 2 predictor variables here. Let's say I want to do prediction at x sub h1 and x sub h2, corresponding to the notation that we first did in chapter 2 when we were doing confidence intervals and prediction intervals for a particular x sub h. And if I want to find then the distance that this particular new observation is to a, let's say, the ith observation in my data set, well, I use Euclidean distance, which just basically means is you subtract the actual data values for each variable, square it, add them up, take the square root. Now, what happens if I have 3 predictor variables, 4 predictor variables? Follow that same path. Just add stuff inside that square root. However, it's often a little bit better to do it this way. Because if you have predictor variables that are measured on different scales, you don't want that scale to have really a detrimental effect on judging distance. So what you could do now is divide by standard deviations instead, or in addition to what we were doing before. Also, what we're going to do is add a weight function here. Because let's say you have 3 nearest neighbors. You might think, well, the nearest overall neighbor is more representative of the observation you want to predict that than the one that is the farthest away of these 3 nearest neighbors. So how about we weight then each observation in terms of the nearest neighbors by a measurement of distance. And so the observations that are the closest will have the most weight. Observations that are the farthest have the lowest weight. So we can now use weighted least squares to actually estimate all these models that we're going to need to have. Let's let d sub q be the distance of the neighborhood's farthest observation. So the one that's the farthest away, let's just so we have a symbol here, we'll call it d sub q. And this q is going to represent the percentage of observations in our neighborhood. So typically, the lowest method, people don't say, let's find the 3 nearest neighbors. Instead, they say, let's find the 10% nearest neighbors, or the 15% nearest neighbors instead. I always use just 3 at first because it's easier to describe. And so here's my weight then that's used in weighted least squares. If I have a distance that's greater than the biggest distance for the observation in my neighborhood itself, give it a weight of 0, meaning that particular observation is going to have no bearing at all on what y hat will be for my observation of interest. For distances that are less than the distance that's the farthest, but still in the neighborhood, I use the following weight. 1 minus d sub I divided by d sub q, cube it, then cube the whole thing. Now, just to give you an intuitive feel for why this is used, what would happen if d sub I was actually d sub q? What would be the weight? 0. And so that we can see that as this d sub I gets smaller and smaller and smaller, closer to 0, that means that the observation is closer and closer and closer to the observation of interest, let's say x of h, and thus it will have more and more and more weight.
Shouldn't the q then be the smallest distance outside the neighborhood?
Yeah, this is the way that the book wrote it up. It's not that serious of a concern. So these weights are always obviously between 0 and 1. Now, what do you use for Q? Should we have 10%, 90%? Well, think about what 100% would be. Well, we're just using regular old weighted least squares. Typically, what's used is 40% to 60%, so 0.4 to 0.6. Q is often referred to then as a smoothing parameter. And you'll see what I mean by smoothing through some plots. Some plots we're going to plot some surfaces, and they're going to be smoother for larger values of Q. So we'll postpone a more of a discussion on it until we get to some plots. Okay. Now, to actually do the weighted least squares estimation, there's actually no distributional assumptions that are used for that. Back in Chapter 1, when we first came across the least squares estimates, we didn't actually use distributional assumptions to come up with those. In the end, they actually end up being maximum likelihood estimates if you have a normal distribution. But the actual derivation doesn't need normality. But unfortunately, what does require some kind of distributional assumption is when you would actually find, let's say, confidence intervals for the expected value of y. You can get around that probably by using some other techniques that don't use distributional assumptions, but this is the only thing that our book talks about. So for example, if you've heard of the bootstrap, one could use the bootstrap here to get around distributional assumptions to find these kinds of confidence intervals. If you want to know more about the Loess method, more than what we go into, our optional book by Fox and Weisberg does contain some information about it. I know when I was a student at Kansas State University, we actually basically had a whole course on robust regression and stuff like this. So you can see it's a bigger topic than just simply one section discussed in maybe about 45 minutes in a STAT 870 course. Now, we've actually even used this Loess method before, but I just didn't necessarily focus on it. In Chapter 6, we looked at these scatter plots. This is for the MBA GUARD data set. And this scatter plot matrix allowed us to understand the relationships between pairs of variables at a time. And if we focus in on one of these plots, so we can really zoom in here. So if we focus in on this particular plot here, the green line represents a simple linear regression model. The red line that's kind of moving around a little bit, that's a Loess model fit. So notice it's no longer straight. And so how this was done was for every single observation that you see plotted there, a y-hat was found, and all these y-hats were joined by a line, and that's why the line is not straight, because different models are used to find each y-hat. The dashed lines then are corresponding confidence intervals for the expected value of y. And so this also then leads us into a use for the Loess method more as a descriptive tool, and that is to help you see relationships. So let's say that the red line was about the same as the green line there. What would that mean for you? Well, a simple linear regression model is a good approximation for the relationship. If, however, you see the red line being a lot different from the green line, then it says, oh, maybe I don't have this linear relationship. And so that's one way that Loess methods are used, more just as a simple descriptive tool. Okay. Here's a good question to put on the final exam. Consider the case of one predictor variable. Why may Loess models be poor at the extremes of the predictor variable? Let's go back to this plot. So why do you think Loess methods may perform poorly when you have an x that's towards the extreme?
Distance will be bigger from nearest.
The distances will be bigger from the nearest neighbors. But I think another, and that's good, I think another way to think about it is this, and I think this is maybe what you're getting at. Let's say that I'm right here. Well, notice to get nearest neighbors, I need to look only to the right of it. I don't have any information at all to the left of it. Where instead, if I'm right here, I can look at all around it. And so because of that then, what happens at the ends, if I were to do a plot of the Loess model here, what happens at the ends in terms of the x's, you can see weird shapes occurring. And that's not necessarily something to be alarmed about. It's just a byproduct of this method. When it finds the nearest neighbors, it can only go one direction versus all around it. Okay, now let's finally get to some numerical examples. So again, what I decided to do was take a look at an example that was in the book and actually expand upon the example that was in the book. And this example deals with a Y, which is the amount of life insurance carried by a person. X1 is their income level, and X2 is their level of risk aversion. So I read in the data, like how I would normally. This is what it looks like. So the first person made $66,000. Risk aversion level was 7. Insurance that they carry is $240,000, I would assume $240,000. So let's begin by estimating a regular old least squares model so that we can compare. So I use the LM function like normal. Here's B0, here's B1, here's B2. Notice that we have positive relationships. And then I can do a plot. Excuse me. Then what I like to do is do a three-dimensional plot of my model. Now to do this plot, I'm actually going to do it a different way than what we've seen before. The reason being is because I'm going to do some plots of this Loess method model 2. And the way that I can get predictions for this Loess method is kind of different from what you're used to seeing. And it coincides to using one particular function R called PERSP, standing for perspective plot, to do this. So to do these estimates, let me actually jump over here to 10. So what I'm going to do is actually come up with a whole bunch of income levels, from the smallest to the largest in the data set by 1. So I use the SEQ function, which we've seen before, standing for sequence of numbers. I'm going to do the same thing for my risk aversion, sequence of numbers from the minimum to the maximum value in the data set by 0.5. And then what I like to do is come up with, let's say, a grid of points. So for every income level, I want to look at one specific risk aversion level. And the way that I do that is use a function called expand.grid. I say expand.grid. I'm going to create a variable called income based upon my income levels. Do the same thing for risk aversion. And so that if I show you what it looks like, we get 1,007 values in there, all the way to the top. And what the grid function does, it takes, for risk aversion level 1, it puts all the income levels that were created by sequence. For risk level 1.5, it puts, again, all the income levels and so on. So all I'm getting is a grid of points so that I can do predictions on each of them. I'm going to use these predictions then to do a plot. I know it's kind of a more difficult way than what we've seen before when we did three-dimensional plots. But again, I need to do this so I can do some nice comparisons to the Loess model fit. So I put all the predicted values then into save.pred. So here they are, all 1,007. Now, before I actually plot it, I need to, unfortunately, I need to reorganize the data a certain way, where I need to put it into a matrix. I'm going to put all the income levels, or the rows of this matrix are going to correspond to income level. The columns of this matrix are going to correspond to risk aversion level. And I want to put then the corresponding predicted value for the row and the column. The way that I can do that is to use the matrix function that we've seen many times before. Here are my predictions: number of rows, number of income levels, number of columns, number of risk aversion scores. By row equal false. What that means is it's going to start filling in this matrix by columns. So when I do this and look at the first 3x3 part of the matrix, this corresponds to a risk aversion level of, let me actually just copy and paste this over here. So for risk aversion level 1, income level 26.852, here's the predicted value. Now finally, I can use this plotting function called PERSP for perspective. My income levels, notice this is just the sequence of income levels that we had from the SEQ function. Risk aversion levels, then my matrix of predictions. Let me do the plot here, and I'll explain the other options after that. And there is now a 3D representation of my estimated model. Okay. Some arguments here. For example, z-axis limits, so z-lim. Tick type equal detail, just make sure that I have the normal kinds of tick marks on my plot, meaning where you see the 70, the 60, the 50, and so on. There are other options available. You can take a look at the help if you're interested. Color equal green 3 for the plot of the color of the surface. And the last important ones are this theta and phi, which correspond to the angle of orientation that you see in the plot. I recommend that you just try different values of theta and phi so that you can see what happens to the plot. If you wanted to look at the plot in three dimensions as we did before using the scatter 3D function, this is what we get. So you can see again, the plane is going through the middle of those points there. One thing I want to point out to you that's going to be important later on is notice that when I go on, look a little bit underneath the surface here, you see a bunch of points that are always below it in comparison to maybe just, you might have one point here below and one point above and so on. But you're having kind of a clump of points that are below it. Pay close attention to that because that's going to pop up later in our Loess model fit. The plot's going to look different for that part of the plot. Okay, so now let's estimate then the Loess model. So I use the function called Loess. Notice that there's no W in Loess, just L-O-E-S-S. Formula equal, here's my response, my two predictor variables, data, span. This corresponds to Q. So we're going to look at 50% of our observations are going to be used every single time when I estimate a model. 50%. Degree equal 1, that corresponds to I want a first order model. If you want second order models, use degree equal 2. I put the results into mod.fit.Loess, and then I just say mod.fit.Loess. Notice you don't see B0, B1, B2 here because there's tons of them, and they will change depending upon what you want for your x's. Let's see here. Number of observations, 18. Here is a residual standard error, which is like our square root of MSE. Do I want to talk about number of observations yet? Hold on. I'm going to postpone discussing the number of observations. We will get to it, but the discussion is kind of long, so I'm going to postpone it. And if I did summary on mod.fit.Loess, you can see that I really don't get a whole lot of good information, unlike what we would get from the summary of stuff from the LM function. You can do names mod.fit.Loess. You can see some stuff that's stored inside of there. Now let's do some plots. So I use the predict function, much how we would in the past, mod.fit.Loess, and I'm going to predict pred.data. This is the stuff that I got from the expand.grid function that we did before. So remember we had 1,007 different rows to this matrix. That's what's in there. I put all the predictions in save.pred, and then I use the PRSP function once again. And this is what we get for our model. So notice it's not a simple plane anymore. It has some curves to it. And again, the reason being is because now for every single set of x's that we have, we're going to use a different model to get the corresponding y hat. Once we get those y hats to do this plot, simply this PRSP function just simply joins all those y hats to form this surface. Now, overall, the surface seems pretty flat, pretty similar to the surface that we had previously, except for we take a dip down there. The reason for the dip was what I was alluding to before. Notice I have a clump of points that are right below it. And so what's happening is that's what's being captured by this Loess model, since it's, remember, just using 50% of the observations. And remember, these 50% are weighted by distance. It's using these 50% of the observations to come up with y hats. And since I have some observations that are kind of clumped down below this plane, this flat plane there, that's why we have this reaction, you could say, with respect to the Loess model. So you can see the Loess model is more flexible, but it's at a cost in terms of interpretation. I can no longer say for every 1 unit increase in income, my response is going to increase by a certain amount. I can't say that anymore. I guess we can talk about this number of parameters. So R provides something in the output that was called equivalent number of parameters. It's listed as 7.62. It's kind of complicated to, at least at first, to fully understand where this is coming from. So here's an explanation. Back in chapter 5 and chapter 6, we first saw this. Y hat's equal to X times beta hat. And if beta hat was for our, sorry, that should be B, corresponding to our notation, vector of our parameter estimates. And of course, B is X prime X inverse, X prime Y. From that, then, we can find what our hat matrix is. And of course, the hat matrix is what puts a hat on Y. So take H times Y, you get Y hat. For an individual observation itself, you could do something very similar, where now you're taking one row of the hat matrix. Now, in the Loess regression model, we're basically doing exactly the same thing. But if we look at one observation in our data set itself, observation I, then what you could do is simply find some kind of linear combination of the y's to get the y hat for it. Let's call this linear combination L sub I. So using that, then, we can put all these L sub i's that we get for all n observations into a matrix called L, and now you have a nice little representation of how to get all the y hats for the observed data values. Okay. Now, let's look at the regular old hat matrix again. What we learned in chapter 5 was that the sum of the diagonal elements of the hat matrix end up being the number of parameters that you're estimating, P. Also in chapter 5, and I'm sure all of you remember this, H is symmetric idempotent. What that simply means is if I were to take H times H, I get H. Also, H transpose is equal to H, symmetric idempotent. Now, the nice thing about symmetric idempotent matrices, and you will learn about this in a matrix algebra class, you take H prime H and then find the trace of it. Does anyone know what the trace of the matrix is? Sum of the diagonal elements. Sum of diagonal elements. You end up with P in this case. Notice how this corresponds to the number of parameters that we're estimating. And so, what this Loess function does, it finds the trace of L prime L. And it ends up being, for us, 7.62. And so that's how it comes up with like an equivalent number of parameters. And you can think of it this way, that essentially, if we weren't doing Loess models here, let's say instead that we were fitting a very high order regression model, what this equivalent number of parameters tells you is how basically high of an order, to some respect, you would actually need in order to get this curvy-like structure. That's what that means. Okay. Let's take a look at page 43. So what I've done here is I plotted on the upper left-hand part the model for first order least squares regression model. In upper right-hand plot, now this is where we use Q equal 0.5. Down below then, I show you what would happen if I use different values of Q. Now again, Q is usually somewhere between 0.4 and 0.6, typically it's chosen. What happens if I went all the way down to 0.2 or 0.8? Let's look at 0.8 first. Notice how that's quite a flat surface. And all these plots are put on exactly the same scale. At Q equal 0.8, it's very similar to the least squares fit. Why do you think that happens?
In this particular case, data is more or less linear.
I'm sorry, that data is what?
More or less produces
Because we have more data, is that what you're saying?
no, because it's very close to the plane.
If I'm understanding what you're trying to, what your point is, I don't think you quite have it. Any other thoughts?
You're using almost all the data.
You're using almost all your data. I don't know. Was that what you're trying to get at?
No.
Okay.
Even if you use all of the data, but the fit of the linear plot is bad, then you won't get right.
Not necessarily, because we are using a form of least squares, weighted least squares. But I mean, if you're using all, see, if I would have Q equal 1 here, I wouldn't get it exactly, but I would get basically what's up in the upper left-hand corner. Remember, the low S is actually using weighted least squares, not least squares itself. But so that's not necessarily surprising to see for Q equal 0.8, I get something very close. So notice how it's more smooth, the plot, for higher Q in comparison to a Q of 0.5 that we had before. This is why Q is referred to as a smoothing parameter. Now if I use Q equal 0.2, so now I'm only using 20% of my data to come up with all my Y hats. Wow, that's just kind of really jumping all over the place. It's less smooth. And you can kind of think of this corresponding to what you learned in your first stat course. When you did a histogram, and let's say you use a lot of classes for your histogram, in other words, a lot of bars, what would that histogram look like? It would be quite jagged, kind of bouncing around and stuff. That's essentially what happens here. The Q equal 0.8 plot then is kind of like using not enough classes, not enough bars to represent your data. It smooths it too much. So that's kind of an example of why we want to maybe use a Q of like 0.5, 0.4, 0.6, something in the middle. We don't want to get too jagged, but we don't want to get too smooth. You're trying to understand the true relationship of what's happening, and by being too jagged, that's almost saying overfitting the model. By using Q equal 0.8, that's maybe underfitting the model. You're missing out on some stuff. Let's do some comparisons of SSE values, sum of squared errors. So what I did for the observed data itself, for the 3 different low S models that we've now looked at, so Q equal 0.5, Q equal 0.2, and Q equal 0.8, get all the predicted values. For the least squares fit, I get all the predicted values. Then I form the sum of squared errors, how you would normally. Y minus Y hat. Square, add them up. And I summarize them in a nice little data frame. So for a least squares fit, I get 8,498. So like about 8,500 for my sum of squared errors. Now remember, the smaller the SSE is, the better the model to some respect. Look at Q equal 0.5. I have an SSE now of 5,000. It shouldn't be surprising because this model now has more flexibility to get to the particular Y's than the least squares method did. And we saw that in the plots. Q equal 0.2. Wow, SSE is going down to 2400. But again, this is maybe an example of overfitting the model. While we like smaller the better, this is maybe too small. What this is saying then is that maybe this, in the end, when you overfit a model, the actual model itself might not work well for, let's say, a new data set that you create, because it's fit too close to the data. Q equal 0.8. Notice how that's higher than what we had with Q equal 0.5. Overall, what do you think about the least squares model? Do you think it provides a good fit to the data? Yeah, I guess you could look at the R-squared. I guess I'm just looking at pictures right now. What do you think? It seems to do a decent job, except for maybe right here. And, depending upon your application, that may or may not be meaningful.
Try an interaction or something, couldn't you?
You could do that, and I was just kind of starting from the point of view of trying to duplicate the example in the book and add a few things, but definitely you can look at interactions, you can look at second-order models, and so on, but let's just take a look at this. I don't think necessarily a second-order model is going to be helpful here. I don't know, maybe it might capture the stuff that's happening down here. We'll make that homework. And lastly here, let's actually look at every single residual. Let's look at the absolute value of every single residual for the least squares model fit and the lowest model fit. And let's compare. Again, with the lowest model, what we saw at Q equal 0.5 was the sum of squared errors was smaller. Let's kind of look at this in kind of a picture form. So what I did here, and we're running out of time, so I'm going to skip over the actual code. We'll just concentrate on the plot. Ask questions about the code if you have it next time. Absolute value of residuals on the y-axis. Residual number on the x-axis. So this is often referred to as an index plot. And so we see for observation number 1, we see for the lowest model, the absolute value of the residual is smaller than it is for the least squares model. Similarly, for observation 2, we see the same thing. It doesn't always happen. So observation 3, we have the reverse. But overall, you see, generally speaking, the lowest model has a y that is closer to its y hat. Sorry, a y hat that's closer to its y, I should say it that way. And that's evidenced when we did the sum of squared errors. So again, what this is saying is the model gets closer to the y's. This lowest model does. Okay, so that basically then concludes what we're going to be talking about in terms of our sections in our book. What we will do next time is just do a final exam review. Okay, so please bring your questions if you have them. We will not, unless for some reason we had a big snowstorm come through on Tuesday and couldn't have class then, we will not have class on Thursday. Okay, so any questions? That's it for today.